Hi everyone, this is EE124 and this is the lecture for November 14. It is recorded on November 10 because I will be traveling on Wednesday. In today's lecture, I'm going to break it into two parts. One is to review the midterm solution. You guys did a very good job in the midterm. It's better than last time. I'm going to post it as another video. Okay, so in this video we will only discuss the rest of the topics of frequency response. It includes the common source again, the common gate stage, the scope, and differential pair. We actually won't have time to go to the feedback circuit, and this is the next topic we are going to discuss in the next class. So not much announcement. For the last lab report, we have posted an announcement in the canvas. There will be no regular report. We don't want you to spend too much time on that. We want you to submit the final report on the day of the lab. So there will be two labs. We only ask you to submit some very simple summary of the lab, and also you need to demo to the TA during the lab to show that you have done it. Okay. And the midterm are graded already, right? You can pick up from my office on Tuesday afternoon or after, or during the November 19th class. Okay, still we will go over the article of the days. This article I find it interesting because nowadays many companies are trying to make a foldable cell phone or a foldable portable device, and Samsung is one of them, which is pretty successful. Right, they announced it that they are going to ship the foldable smartphone next year. But actually, at the same time, there is a startup called Royal, and that they actually start doing the similar thing, and actually they announced a few weeks, I guess, before Samsung that they are going to ship this, and it is expected that they are going to supply this to many Chinese cell phone makers. Right? So now you see there are lots of new stuff nowadays, and they like the Samsung one, I guess they all use this AMOLED, active matrix, organic LED. They have very sharp contrast and also foldable, and this is something that you will see in the future. And they are actually have a lot of private financing to this company. So because this is very promising. Okay. So you see that electronics is everywhere, and definitely for this foldable displays, you need a lot of analog circuit, and now you have to consider how this stress or bending is going to affect the transistor performance. Okay, let's start our topics, right? So before the midterm, right, the last topic we have discussed is actually how to find the high frequency response of a common source amplifier. Common source amplifier. And at that time, what we did is we tried to use Mueller theorem. Let me turn on the laser pointer, right? So we have this common source amplifier, and we say that first we use a Mueller theorem. We decompose the gate drain capacitor, right, into two capacitor using the Mueller theorem, right? It becomes C1. It becomes this C1 rule 1, right? It was CGD, so it's CGD times 1 minus the gain. The gain we know that is negative GMRD. Okay, so it is CGD1 plus GMRD. And then we have another one is C2, CGD equal 1 plus 1 over GMRD, which is 1 minus 1 over negative GMRD, right? And then we can use the method we have learned for each node. We will try to find out what is the equivalent resistor and also the equivalent capacitance, right? And then we say that the pole is going to be the equivalent resistance. For example, the input, this is the node. We have an input resistor Rs, and then the equivalent capacitance is what? CGS in parallel with C1, and this C1 is the Muller capacitance. So that's why this was CGD times 1 minus negative GMRD, 1 plus GMRD, that is, right? And this is the pole. So what does it tell us? A very important thing in common source amplifier is that the CGD is amplified by 1 plus GMRD. So effectively, we have a lower pole because we have an effectively larger capacitance in the input, right? And similarly, we do this for the output node, right? The output node, we see we have an RD, and some of you will claim, hey, we also have R0, right? Here we assume R0 is very large, infinity, right? Otherwise, it will be RD in parallel with R0, R0, right? So this is only RD here. And then for capacitance, we have CDB, and then plus CGD, which is times 1 plus 1 over GMRD, right? This one is this one, right? It is this 1 minus 1 over A. And if GMRD is very large, what will this term be? 1 over a very large term, right? GMRD is very large. This is almost 0. So for output pole, the pole doesn't change much because this term is almost 1 if GMRD is very large. Okay, so this is a simplified method to find the poles, right? Now, is this accurate? This actually serves some very critical purpose. It helps us to gain the insight of this circuit. At least by not doing very complicated small signal model analysis, I already know that my input pole is going to be very low because of the CGD times 1 plus GMRD. We have this Muller effect, right? But in reality, if you need to find out the accurate solution, you need to write down this small signal model, right? So remember that this is the small signal model, and you see here we have, this is what? This is source, right? This is, this is gate. This is gate, right? This is the drain, this is the source, and source is grounded, right? So we have this VGS, which is just Vx, so this is GMVx, right? And then we put the capacitance here, right? And then what we need to do is solve the KCL and KVL, right? And we will get this equation. So basically, this is the transfer function. How V out is related to the V in, H of S. Okay? So you see that it's very complicated. Especially in the denominator, we just put it as AS squared plus BS plus 1. But A is this very long term, and B is this even longer term. Right? So was what we did correct? It's difficult to say from here yet, right? But at least we see that one thing we are missing is that in the previous method, we only found the poles. We have 2 poles. But here, we actually have a 0. We cannot find the 0 by using the method we have found, okay? So what is the 0 here? Remember what's the definition of 0? 0 is to set the numerator to 0, right? That is CGDS minus GM times RL equal to 0. So S equal to GM, you move to the right hand side, divided by CGD. This is the 0. This is the 0. Omega 0. Okay, this is the 0 of this circuit. So first thing, Muller analysis, or the analysis we did, we actually missed this 0, right? Remember the Mueller capacitor is what? Related to CGD, right? That is the one we applied the Mueller capacitor. But we definitely missed the zero here. Okay? And how about the poles? How do you find the poles? By definition, right? So this is a full solution. This is a full solution, complete solution, right? So we just follow what we learned before. To find the poles, we need to set what to zero? Denominator, right? Which is as squared plus bs plus 1 equal to 0. How do you solve this? Well, you know, it's just s equal to negative b plus minus square root b squared minus 4ac divided by 2a. And c is equal to 1 in this case. Right? This is what you learn maybe in high school or middle school to solve the quadratic equations. Right? So it's very complicated, and we cannot gain the insight much. Right? But anyway, this is how you solve it. Okay? So, and I can tell you, it's not equal to what we got in the previous slide. Okay? It means our approximation is really just an approximation. Remember why? Do you still remember why Mueller effect is just, Mueller theorem is just an approximation? If you try to trace the derivation we have done, there's no approximation actually, right? And the main reason is that we actually use this A is the DCA. But in reality, the gain changes at higher frequency, right? So that is the source of the approximation, right? So in the derivation, as long as our A is correct, then this is correct. However, we always use the DC gain as a gain A, DC1. That's why this is an approximation. Okay, so what you need to take home is that it missed the zero, and also the pole is just an approximation. Okay, so that's what you need to learn so far. Okay, now we were saying that let's go to another part. What we want to do is that now how do I solve this equation? This is pretty complicated, but you can solve it, right? You use Mathematica or whatever software, or use your or do it manually. You can solve it. But there is an approximation that we can solve it. So how do we solve it? Remember we say that we want to set as squared plus bs equal plus 1 equal to 0, right? And then we are going to solve it. But we are going to do something called dominant pole analysis that can help us speed up the process and also to gain the insight. First of all, this one can be written as 1 minus, let's say 1 plus s divided by omega p1 times 1 plus s divided by omega p2 equal to 0. So this is not exactly correct. It's from the textbook. I think more accurate, we should say minus 1 minus s divided by omega p1. So that omega p1 are the poles, right? But it's okay. We're just playing with the absolute number. So in the derivation here, so let's just follow its approach, right? Omega p1, omega p2 are the poles of the circuit, right? Right. So this is just to write, you can always write a quadratic polynomial as 1 plus s divided by omega p1 times this one, right? And by definition, we say we need to set this one to 0. So the s, omega p1 and omega p2 are the poles, right? Let me put absolute value just to avoid any ambiguity. Okay, so based on this, I can show that I just expand the do the multiplication. This becomes 1 plus s divided by omega p1 plus s divided by omega p2 plus s squared divided by omega p1 omega p2 equal to 0, right? I just multiply 1 to 1, 1 to S divided omega P1, and then S omega P2 to 1, and then S omega P2 to S divided by omega P1, and I get this. And then you compare these two equations, this one and this one. Compare. What do you see? 1 equal to 1, of course, right? But what is B? B equal to 1 divided by omega P1 plus 1 divided by omega P2. And what is A? A equal to 1 divided by omega P1, omega P2. Right? I just compare the coefficient of S and S squared. Okay? Now, that is what we, the next step, look carefully. Now we call, assume what? Omega P2 is much larger than omega P1. What does it mean? It means that if I have a OD plot, I first see this omega P1, and then eventually I see omega P2, omega P1, omega P2, right? So this is how many? This is 20 dB per decade, right? And here it becomes 40, should be negative 20 dB, 40, negative 40 dB per decade, right? So if omega P2 is much, much larger than omega P1, what does it mean? It means omega P2 is much, much smaller than omega P1. What it is saying is just saying that the pole are very far away. For example, this may be 100 hertz, right? Let me write here. And this may be, let's say, 10 megahertz. And of course, 10 megahertz is much, much larger than 100 hertz, right? So what does it mean? It means omega P1 is a dominating pole. That's why we say this is a dominant pole analysis. So that means P equals to 1 divided by omega P1 plus 1 divided by omega P2 is equal to what? Approximately, because 1 over omega P2 is smaller than 1 over omega P1. That means this is almost 1 over omega P1. So with this, then I know that omega P1 is just equal to 1 over B. Right? So this is very good. We don't have to solve these complicated quadratic equations to get omega B1. I know that if one of the pole is dominating, much smaller than the other one, then I know that the dominating pole is 1 over B. So for this one, what does it mean? It means for this common source amplifier, the dominating pole is B. B is this one. So what is this? 1 plus GMRL CGD plus CGS, and then the whole thing times RS, right? I just take the RS out, right? And then plus RL CGD plus CDB. Okay? What is this one? This is exactly what we got before. Remember, this is RS CGS plus CGD times 1 plus GMRD. RS CGS 1 plus GMR. Sorry, this is RL. Yeah, RL CGD. So you see that by using Mueller analysis, we miss this term. Right? We miss this term. RL CGD CDB. Right? So this just to tell you that the analysis we did actually is an approximation, but it's okay because this term is going to dominate because of this large GMRD. Okay? And at the same time, we introduce another methodology called dominance pole analysis. Now, I know what is omega P1. And what is omega P2? A equal to, see this one, right? omega p1, omega p2. So what does it mean? It means omega p2 equals to what? 1 over a times omega p1. And do we know omega p1? Yes, we know already. This is omega p1. And we also know what is a, right? So by doing this, I will be able to find out what is a. And of course, since omega p1 is also equal to b, this is also equal to b over a. Okay? Omega p2. So this is the equation you want to memorize. Omega p1, the low pole equal to 1 over b, and then the other is b over a. Okay? But you don't need to memorize other equations. This is just something you really need to know about this dominant pole analysis. If you have taken any analog circuit, you should know this one. Otherwise, it means you still don't know the analog circuits, right? It may ask you in the interview also. Okay, so we have gone through the common source amplifier, right? By itself is nothing special. We know that we can use this approximation, find the equivalent R, right? Find the equivalent C, then we find the pole. But if you have a capacitor connecting two nodes, both are not at ground, none of them are at ground, then you need to use Mueller theorem. And you find that for common source amplifier, the input pole actually reduced because the effectively larger capacitor, right? And then we also say that this is just an approximation, and you want to solve it. If you want to get the full solution, complete solution, you need to solve the small signal model, right? And you realize that we are missing the zero, and also the pole is not exactly accurate. But how do you solve it? The only way that you can solve it is, not the only thing, the best way, one new method you just learned is dominant pole analysis. If we can assume one of the pole is much larger than the other, then we can use this approximation. The first pole is 1 over b. The second pole is b over a. And that's it. Okay? Now with this, then let's move ahead. Now my goal is say, hey, how about the input impedance, right? Would this be difficult to solve? This should be very easy, right? Because we already know how to break down. We can change this one to what? We have a what? This is a capacitor. We can use Mueller effect, and we say this is equal to CGD times 1 plus GMRD, right? And because of this, so Z in will be equal to what? What is the input impedance? Right? We remove this and use Mueller capacitance. So the C in, of course, is equal to 1 over, let me just call this C1, right? S times CGS plus C1. And what is C1? C1 is CGS plus CGD times 1 plus GMRD. Okay? So you see the Mueller capacitor not just help us to find the pole, but also can help us to find the input impedance and output impedance. Okay, good. So we are done with the common source amplifier. Now we are going to another part called common gate amplifier. Right? This is one thing very special. So for common gate amplifier, you attempted to use the same method we have learned, right? But sometimes some circuit you cannot use those methods. For example, here, how do you find the input pole? The C is not connect to ground, right? The capacitor. So here you cannot use the simplify RC method. Then how do we find the frequency response? All you need to do is just solve the small signal model. Okay, difficult, right? Not easy. But we don't need to, for this particular circuit, we don't need to draw the small signal model. This is it. What we can do is, what is Vx? Right? If we know Vx, we know what is the relationship between Vx and Vout, because Vx to Vout, Vx to Vout is just what? It's just input is Vx, output is Vout, and gate is a constant bias, right? Let's just ignore this part. Ignore this part. If Vx is the input, what is this? This is what kind of amplifier? We know it is a common gate amplifier. What is the gain of common gate amplifier? Vout divided by Vx equals to Gm RD. We know that, right? It's Gm RD. The point is, what is the relationship between Vx and Vin? This is the difficult part, right? This is an ideal current source, so we can make it open circuit. So all we need to know is, what is the input impedance? Looking up, what is this? Think about what is the input impedance of a common source, common gate amplifier. Let me call this Rx. What is this? Yes, Rx equal to 1 over Gm, right? So Vx equals to V in potential divider 1 over Gm divided by 1 over Gm plus Rs plus 1 over Sci. This Rs plus 1 over Sci is the impedance of Rs in series of Ci. Okay, so now I can plug in this into here. My goal is to find out what is V out divided by V in. V out divided by E equal to V out divided by Vx times Vx divided by V in, right? So what is V out divided by Vx? We already say that is Gm RD. What is Vx divided by V in? Just this equation, right? So this 1 over Gm divided by 1 over Gm plus Rs plus 1 over Sci. So this is just what? Rd, right? Because the Gm cancel, 1 over Gm plus Rs plus 1 over Sci. Okay? So why do we want to go over this exercise? To a few things. One, you want to understand just to the first thing is to practice again how to find the gain easily by inspection, right? Full potential divider. And also this time we incorporate the frequency response because 1 over SC1 Ci, right? Another thing is to understand the property of common gate amplifier for low frequency response, right? So we can plot the body plot of this guy, right? So this is the gain, this is the frequency, this is the gain, equal to V out divided by V in. So imagine when frequency is very, very small, what happened to this one? This is almost 0, 1 over S. S is just J omega, right? We can put J omega. S is almost 0 when it's very small. If it's very small, almost 0, then it means what? The whole thing is very large. This is very large. So it's dominating. So as a result, you actually have a high pass filter with 20 dB per decade. Okay? Until at a point, this one becomes very large, so this can be neglected, 1 over S, right? Then you will flat out. It's not dependent on the frequency anymore. And this is when what? It has a value of Rd divided by 1 over Gm plus Rs. Right? Because 1 over Sci is very large. Right? So you see that the low frequency response of this circuit is a high pass filter. Okay? And you can also prove that the pole of this one is GM divided by 1 plus GM RS times RC1. How do you do that? Just set the denominator equals to 0. Then you will get this one. Okay, good. Now let's go to the high frequency response of the common gate amplifier. How do we, it's not too difficult, right? We have this first, we have this circuit. We remember this circuit. Okay, let me make sure recording is in progress. Right, we have this circuit, and at high frequency we're going to short the C1, right, because it's a large capacitor. So we have this one. Remember, V in go to RS, and then you have a voltage source, current source, which will be open. Then you have this resistor, transistor and resistor. Gate is biased, so this is the common gate amplifier. Then you will add the 4 capacitance as we have discussed before, right? And now I'm going to simplify. How do I simplify? I'm going to ground the constant voltage source. Because I ground them, then what happened? This node goes to ground through CSB. This node also go to ground through CGS for X, right? For Y, this node go to ground through CDB and also go to ground through CGD because VB is grounded. So I can just what? Just combine them together, right? So this one becomes a big capacitor with CDB plus CGD, right? And this one is grounded, and then this is Y. Then I have X, also have a big capacitor CSB plus CGS. And then I have a resistor here, V in RS, right? So very simple. And how many nodes do I have? I have 2 nodes, X and Y, right? So what is the pole at X? Omega P1 or omega Px equals to 1 over Rs times, this is confusing, let me redraw it. We have 2 poles, X and Y, right? And we have CSB plus CGS times Rs. And then for Y, what do we have? This is RD, right? We have RD times CDB plus CGD. Okay? What's so special here? You see that we don't have Mueller effect in common gate amplifier. This is very good because there's no capacitor connecting the input to the output. Okay? Another interesting thing is this one. Omega Px is 1 over Rs CSB and CGS. This is almost equal to 1 over Rs times CGS. Right? And at this stage, you see that I make a very big mistake. What is the resistor at node X? I say it is Rs. Is it right? Actually, I'm wrong, right? Because it is Rs parallel to what you looked up. And what you looked up is what? GM. So sorry for that. It should be Rs parallel with 1 over GM. So if Rs is much larger than 1 over Gm, this one becomes 1 over Gm. And this is what? Gm times Cgs. And I here ignore C, SB, and also Rs. And what is this? Remember, this is the transit frequency of the transistor. Remember, what is the transit frequency? Transit frequency is the frequency at which you have the Gm equal to 1. And transit frequency is telling you the limit of how fast the transistor can operate. If transit frequency is, let's say, 100 gigahertz, then don't dream that you can have a circuit that built from that transistor that can operate faster than 100 gigahertz. And now it's telling you that the input pole of a common gate amplifier is similar to the transit frequency. So it's basically saying that the input pole has no effect on the circuit, because any circuit built from this transistor should not operate faster than the transit frequency. And the input pole is the transit frequency. So there is no effect on the circuits, because there will be other pole that is dominating. And in this case, omega py is the dominating pole. Okay. So two message here, right? Of course, we did the exercise, that's good, right? And you see I did something wrong. It should be Rs parallel 1 over Gm for this resistor. Need to be very careful, right? Two things to take out. One is that there's no Mueller effect. Another is what? The input pole is about equals to the transit frequency for a common gate amplifier. So it means it's dominated by the output pole. It means the input pole is very, very high. Okay. Now I want to move forward to talk about the Cascode amplifier. For Cascode amplifier, do you remember what is a Cascode amplifier? We will have a bias transistor on top of this common source amplifier, right? So we have very large R out, and Gm is still Gm of M1, right? And then we try to see what we are afraid of is the Mueller effect, the Mueller capacitance. Because from common source amplifier, we know that we have a very large Mueller capacitor, which is CGD times 1 plus GM RD, right? Do we have this problem here? If we have this problem here, that would be very bad, because we know that our gain, right? We have large gain. So it is very bad if there is Mueller cap, right? But luckily, we actually have very small Mueller cap. Why? Because the capacitor going to have this effect is connected from the gate to the drain of M1. But this is not the output. This I don't write it here, because if right here you will get confused. This is not the output. What I'm trying to say is that Y doesn't have a very high gain. What is the gain from X to Y? What we need to do is just saying that, okay, CGD1 will become a Mueller cap, right? Of what size? Of CGD1 times 1 plus 1 minus the gain, right? Minus A, right? The question is, what is A? A, of course, defined by Vy divided by Vx, right? So this is just a, so we can look it as this way. So this is just what? What is this? This is just a common source amplifier. And what is the low for this one if Y is the one we want to look at? This one, what is the capacity resistance? This is 1 over Gm. 1 over Gm2. Right? We try to see the first. So what are we doing? See M1 as common source amplifier with Y as output, right? Is it correct? This is the input, so this is the output. And M2 as RD, the low. But the low is what? RD in this case, we're looking up, this is just equal to 1 over GM2. Okay. So as a result, A equals to common source amplifier negative GM1 times RD, which is your negative GM1 divided by GM2, which is almost equal to negative 1 in most cases. So if this is the case, what is our Mueller cap? So if I try to put this as a Cm Mueller cap, then Cm will be equal to CGD1 times 1 minus negative 1 equals to 2 CGD1. Small. Okay, this is very good. It tells us that Pascal amplifier doesn't have the trouble of large Mueller cap, right? As I said, it has very large gain. If it has a big Mueller cap due to the large gain, it is very bad. Luckily, no, it is very small. So this is a good thing about Pascal amplifier. Okay. Then how about for the poles for Pascal amplifier? So what we need to do is just to draw the poles, right? Draw everything. And this is pretty time consuming. I decided not to do it here. You can find it easily, right? Just do it as exercise and find the solution from textbook. Okay, if you cannot find them, let me know. I can scan to you, right? So, but you know how to do it. Basically, just add 4 capacitor to M1, right? 4 cap. And then add another 4 cap to M2. And then what? And then use simplification. What is the simplification? If they're connected both to the same node, they have no effect. If they're in parallel, combine them and then combine with Mueller effect, right? And we learned that what Mueller effect we have already. This is CGD1. We already showed that it will give you 2 CGD1, right, when you break that. In particular, I can show you that this one is 2 CGD1, and same for this one, also 2 CGD1. Why? Because this is just CGD1 times 1 minus over 1 over A, which is, because A is negative 1, so this is again 2 CGD1, right? A equal to negative 1. So they are the same. This is the time the input and output have the same Mueller cap. Okay? And sorry, actually no need to refer to the textbook. So here I show you the results. This is after simplification, right? So actually, on next page, you can go to the next page to see the results, right? And I do show you this is not exactly 2 CGD1 because I'm using I'm using this we don't assume GM1 equal GM2, right? But usually you can say they are similar, or here you keep it. And then with this, then we can find the pole. What are the pole? Let's try to find it, right? We have 3 poles. Okay, we have omega x px, which is equal to, let me call this cx, 1 over rs times cx, right? No problem. This is easy, right? Or py, I'll call this cy. The point is, how do you find the resistance? Going down is R naught, going up is 1 over gm. So this is 1 over gm times 1 over gm2 times cy. Okay, and then finally, omega pi out, this pole is what? Is equal to 1 over RL times CGD2 plus CDB2. Okay, so nothing special. You see, even for cascode circuit, it's so complicated. You just follow the procedure carefully, you can find the free poles very quickly without solving the small signal model. Okay, and we also have the input and output capacitance, right? So what is the input capacitance? Input is here, right? And I will see is RS, and then in series with the C, right? So let me call this C1 again. So, or CX, I should call it CX. So Z in equals to RS plus 1 over S times Cx. Okay, and how about Z out? Z out, we look back, Z out, this is becomes RL. This time is in parallel with 1 over S G C G D2 plus C D B2. Okay. Finally, for differential amplifier, looks very complicated, right? But after all, remember we can use half circuit technique, then it is just the same as common source amplifier. We have exactly the same equation. Okay, so just to let you know about this. And for source follower, the only thing we want to say is that because of the strong interaction between X and Y, we cannot treat it, associate the pole to each node, right? Actually, in the common source amplifier, we already see that there is some modification, right? If you go back to this slide, remember this is the pole. We try to associate this pole to this input node, but no, we actually have some interaction. You see, we have RL, CGD, CDB. Same for source follower, but because of the way it operates, we cannot treat it in this way. We need to solve the small signal model. Okay, so this is the main message I want you to take home. Some circuits cannot solve by the method we use. So you have to be very cautious about doing this. Okay, and then you solve this one. Okay, and try to do it yourself to solve the small signal model. Okay, so that's it for this part. And please watch the video in which I discuss the midterm result. Thank you.